Hello friends, welcome to the topic synchronization examples or classical problems of synchronization in the subject CS 3451 Introduction to Operating Systems. Here we are going to see three problems. The first problem is bounded buffer problem. So these problems are called classical problems of synchronization. The first problem is bounded buffer problem. The word bounded is nothing but a limited. We have a buffer. Buffer is a temporary storage which is bounded. Bounded means it has a capacity. So here example is n. Suppose n values 10 means we can maximum store 10 elements or 10 data in the buffer. So the buffer is a bounded buffer. It can hold a maximum n items. So n is 10 means that 10 items maximum we can store in the buffer. Here we got two processes. One process is called the producer, another process named as the consumer. What the producer will do, it will produce or store items into the buffer. So producer is going to add or store or put items or data into the buffer. When a producer can produce items, the condition is if the buffer is not full or there is some space in the buffer. Okay, that is one condition. Then second process is consumer process. It is going to take or consume items from the buffer. Here, what is the condition? The buffer should not be empty or it should contain some items. So these conditions we need to satisfy whenever the producer and the consumer are accessing the same time the buffer. We need to ensure these conditions should not affect these two processes. Okay. So we are going to provide a solution for this problem using semaphore concept. So three variables we are using: mutex, which is for a mutual exclusion. That means at a time, either producer or consumer can access the buffer. Both cannot be accessed at the same time. For that, a mutex is used, and then variable empty is used. Initially, it is equal to n. It is initialized with the value n. N is the capacity. So at starting, there will not be no items in the buffer. So empty becomes n. And then full is another variable. Since no items in the buffer at beginning, so full is equal to 0. Okay, so these three variables we are using for the solution of bounded buffer problem. So two processes we see in a producer and the consumer. So producer going to produce items when the buffer is not full. So that we are going to check in this coding. This is a producer process coding. So it's a do while loop. Initially, producer produces an item in a variable. Next step is a variable. Suppose consider here a value 10 will be produced. That 10 we are going to write it in the buffer. So here 2 wait operations we are executed by the producer process. One is wait of empty, wait of mutex. What is the use of wait of empty means? We told a condition no. Whenever the buffer is not full, then only producer can produce the item. So that we are checking this wait of empty. Is there is any empty space in the buffer, then it will go to next statement, wait of mutex. When we are executing this, at the same time, consumer will not be allowed. For that, this wait of mutex. If both are true or both are satisfied, then the producer can add the value into the buffer. So in the next step, already we have data item that will be added to the buffer. After adding the item data will into the buffer, the producer executes two signal operations. One is signal of mutex. This is to allow the consumer process to consume the item. And then signal of full. It indicates one item is added in the buffer and informs the consumer items are available in the buffer. For that, signal of full. It is the structure of producer process. Next is this consumer is the structure of consumer here it is given. So the consumer process coding. Again, it's a do while loop. So here initially we got 2 wait operations. Wait of full. That means it indicates whether the buffer contains some items. In that case, it will be executed and come to next statement, wait of mutex. Now consumer is going to consume item from the buffer. At the same time, producer should not be allowed. For that, this wait of mutex. If both are executed, then we will come to next statement. Here, the consumer going to remove one item from the buffer. Okay. After removing or after consuming, the consumer executes the two signals. Signal of mutex. Now the item is consumed, so the consumer can allow the producer to produce next item. So that is signal of mutex. and a signal of empty. Since one item is removed from the buffer, so it has to be decremented. So signal of empty. The buffer space is now empty now. That is indicated by the consumer. Okay. The consumed item can be taken into the variable next to C. So by using these two coding, we can solve this bounded buffer problem. This is the first problem for a classical problem. The second problem is reader-writer problem. So here consider a data object or a variable. It is shared by many processes. Suppose there are 5 processes sharing the data object. Among the 5, some process wants to read the content. They are called a reader process, and other process wants to update the value of that data. They are called a writer process. Among the 5, consider 2 writer processes there, 3 reader processes there. So here we have some list of conditions. The first one is any number of reader process at a time can access the data. So we have 3 reader process. When we allow all the 3 reader process to read the data object, no problem will come because all are reader process only. The second condition is during the write operation, read is not allowed. Suppose a writer process going to access the common data, at the same time we should not allow a reader process because the data will be mismatched. The third condition is during one write operation, another write are not allowed. Okay. So if one writer process going to update the value of this data object, at the same time we should not allow other data object because the result may be inaccurate. Okay. So these are the 3 conditions. The first condition is many read can be allowed at the same time. During a write, read is not allowed, or during read, write is not allowed. Third one, during one write, another write is not allowed. So this we need to satisfy, or we need to provide solution for this. So here 2 processes are there, reader process and a writer process. Okay. So here a list of variables we are using. So 2 semaphore variables we are using, semaphore mutex and write. So mutex is initialized as 1. The write also initialized as 1. And then read count, it's an integer variable. How many processes currently doing a read operation? That is initialized as 0. Okay. Here we have the structure of writer process. So in this coding, we are going to ensure this third condition. During one write, another write is not allowed. Okay. So come, just example, take, we have 2 writer process. Suppose the first writer process going to modify the value of that data item. So it will execute, the first writer process executes this coding. It's a do while loop. First statement is wait of write. So write is a semaphore variable initially 1. During wait of write, the first, since this is positive, the first process can be allowed to perform the write operation. At the same time, the write will be changed as 0. Okay. Now, at the same time, the second writer process want to perform write operation. The second process also execute the same coding. It executes statement wait of write, but now the write value is 0. That means already one process already doing the write operation. The second process will not be allowed to perform write. So second process will be in waiting state now. Now first process is doing this. Once the write operation is over, it executes a signal of write. During signal, the wait is again changed as 1. Okay, now the wait values, the write value is 1. Again, consider the second process, second writer process. It checks this wait of write. Now write is 1, so it can be allowed. So after completing one writer process only, other writer process allowed. At a time, 2 writer processes are not allowed to access the common data. So third condition, this third condition is satisfied by this coding. And then the next coding is the reader process coding. Here we are going to satisfy the first 2 conditions. Multiple reader process can be allowed. During read, write is not allowed, or during write, read is not allowed. Okay, we will check that. So this is the structure of reader process. Suppose consider R1. R1 is the first reader process, executes this. So it's a do while loop. First statement wait of mutex. Initially mutex is 1. So R1 can be allowed to enter into next statement read count plus plus. Now first process going to perform a read operation. Initially read count is 0. Now it will be 1. If read count is 1, wait of write. Now this condition is true. Now read count is previous statement, it becomes 1. So this equals true. So wait of write will be executed. Wait of write means Now we are going to perform read operation. So we should not allow any other write. For that, we are doing this. So wait of write means during read operation, we have to block the write operation. So write is blocked. Automatically, the second condition is satisfied. During read, write is not allowed. Then signal of mutex. Initially, mutex, after this statement, mutex becomes 0. Now, after signal of mutex, mutex becomes 1. Why we are changing means now the reader process R1 is allowed to perform read operation. Consider R2, some other reader process. Again, that R2 executes the same coding, wait of mutex. So mutex is already 1 after the signal of mutex. So R2 also allowed to enter into next statement. Read count plus plus. Now R2 also going to perform read operation. Read count is 2. Now this is not executed because read count is 2. Now this is skipped. Then signal of mutex. Again mutex becomes 1. Again some other reader process can be joined. Like that, any number of the reader process can be allowed at the same time. So that ensures the first condition. Multiple read can be performed. So here reading is performed. So all the reader process and read at the same time. Okay. Once read is over, again we have to decrement the read counter. Here decrementing, whenever the read count becomes 0, we should allow writer process to update the data. For that, a signal of write is given here. One signal of write is given, that ensures that all read operation is over. Now writer process allowed to perform write operation. So this is structure of reader process. So using this and this writer process thing, we can able to solve this problem, readers writers problem. And then the third problem is dining philosopher problem. Here we have a dining table. In the table mid we have a bowl with rice. Rice is there. Surrounded in the table 5 philosophers. 5 philosophers are sitting. Their task is thinking and eating. They will think and eat. Okay. So there are 5 chairs. In the 5 chairs, 5 philosophers are sitting. Their task these 2. Okay. So in the table, a bowl of rice is there and 5 single chopsticks is there. There will be chopsticks. Only 5 chopsticks are there. Whenever a philosopher is hungry, he has to pick up 2 chopsticks that are closest to him. Suppose a philosopher is hungry, 2 chopsticks are needed to eat. One is available in the left side, another one is available in the right side. So nearer to him, chopsticks are used for eating. Okay. So this is structure. Dining table, we have rice. Here are 5 chairs, 5 philosophers are sitting. So this one is a chopstick. There are 5 chopsticks in the table. Suppose consider whenever this philosopher is hungry, he has to pick up this chopstick and this chopstick for eating. Okay. Suppose this chopstick is currently used by this philosopher, then if he has to wait until the chopstick becomes free. This is a problem. So we are going to solve the problem using a simple coding. So here we are using semaphore whose name is chopstick. Since we have 5 philosophers, we are creating that variable as an array, chopstick of 5. All the array variables are initialized with the value 1. Okay. So this is a structure of every philosopher. Whenever a philosopher wants to eat, he has to pick up 2 chopsticks. So for that, we have 2 operations, 2 weight operations. Weight of chopstick of 5. This is to take left side chopstick. This is to take right side chopsticks. So if when these 2 chopsticks are free, then the philosopher can take. If both are available, the philosopher can eat. After eating, he has to release both the chopsticks. So that the 2 signal operation. To release the left chopstick, to release the right side chopstick. After releasing, again the philosopher will enter into thinking state. So this is a simple coding to solve this dining philosopher problem. Okay. Best solution for this problem to free from deadlock is instead of 5 philosophers, we should allow 4 philosophers maximum. And then allow the philosopher to eat when both the chopsticks are available. And another condition is odd position philosopher to pick up his left chopstick first and then right. Similarly, the even position philosophers, okay, to pick up right first and then left. If we follow these, we can avoid from deadlock. Okay. So these are the 3 problems. These are considered as classical problem for synchronization. First one is bounded buffer problem. Second one is readers writer problem. Third one is dining philosophers problem. Thank you.